Hi, welcome to Integrated Science. Today we are going to continue talking a little bit about the stages of a star. Went through that yesterday, introduced some new terms: nebula, protostar, main sequence, red giant, supernova, black hole. Kind of go through that again with some of our notes, just so that you can kind of add that into your wheelhouse of information, just to make sure that you feel really comfortable with it. So these are the Google notes Doodle notes, sorry, that I would normally give you. And as you can see, I'm kind of going through just a couple of different things here. So just so that you can kind of see a timeline of it. So first thing is how stars are born. Once again, they're not living creatures by any mean, but they do go through a cycle, just like you would go through a cycle, such as you were an infant, and then you were a toddler, and then you were a child, a young adult, to adulthood, and then further on. So stars can kind of do that as well. So let's just kind of go through and kind of revisit some of these ideas. So stars are formed in a nebula, which is a cloud of gas and dust. The gases contract, they push together, and they start to spin, which flatten into a disk. The disk spins faster and faster, attracting more gases and creating a hot, dense core called a protostar. So that's a lot of information there. So just think of that accretion process, is that they're starting to clump together, and as material gets closer together, you also get that heat that is starting to ignite, and you get our protostar, whereas fusion is really trying to start to take place, and that's where this says here, is that when it gets hot enough, it begins nuclear fusion. And remember, that's 4 hydrogen bumping into each other to produce helium. And once it does this, once it starts fusion, after thousands of millions of years, it is now a star. So it's entered that main sequence stage. Once its fusion process of hydrogen to helium is over, then unfortunately it starts to die off just a little bit. So remember, we talked about mass matters with a star, and so we're going to talk about our small, medium, and large size stars. So let's look at the small one first. So the outer layers in a small star are going to expand into our red giant. And as it does that, the core tries to collapse on itself. And as it does that, it leaves lots of gas in the outer area called a planetary nebula. So it circles back to that nebula. So the small star is going to give another nebula that's going to have enough stuff to hopefully create a solar system if readily available. And then the outermost layers, it's going to eject and then leave a white dwarf at the center. So in a small star, once it leaves the red giant stage, those outer layers are going to leave a nebula for possibly planets to form, and then the remnants of the core is the white dwarf, not producing any energy, just releasing energy. And once it releases all of its energy, it then becomes like a black dwarf, which is just pretty much a cinder of what was left floating in space. Our large and massive stars are a little bit different. Large and massive, they'll go into that red giant stage as well. Then once it has fused, remember, it'll go through fusing hydrogen to helium, helium to carbon, carbon to silica, all the way down until it hits iron. Iron is that important element, and once it reaches trying to fuse iron, it physically can't. Iron is too stable, so it explodes into that supernova. And that's what this says here, causing a supernova explosion. And in the midst of that, depending on if it is a large to medium-sized star, it's going to leave a neutron star and another nebula for either a star or maybe planets to form, but it leaves a nebula that has some building blocks in it for matter to condense back down. If it is a really, really large star, a supermassive star, sometimes it is too massive, and instead of exploding, it implodes, and it creates what we call is our black hole. And once again, that is definite, the most massive thing. Nothing can escape a black hole, not even light. And we can physically see pictures where light is orbiting around, and then it doesn't just keep orbiting around, it just kind of just dissipates. So once it gets to that center, and we'll talk about this singularity, nothing can escape it. So just to revisit some pieces of information that we talked about with the sun and its layers, is that all stars have these types of layers too. So let's just look at this picture right over here. So we have our core, our radiative zone, our convection zone, our photosphere, and our corona. So remember, core, radiative, and convection are kind of the inner layers, and then photosphere and corona are our atmosphere layers of the sun. Core is where nuclear fusion is happening. That's a really important spot. And as it does that, it produces tons of energy that gets radiated up through the radiative zone. Once it reaches the convection zone, it starts to cause energy being moved through our thermal dynamics of that circular motion. The photosphere is then heated up, and this is the layer that we can see every day. Here's a mess today. And then finally, the corona is the outermost wispy layers that we can only see normally during an eclipse. So it says less dense, but the highest temperatures. And actually, we'll talk about our Parker shuttle that is orbiting around the sun, trying to figure out why is the corona so much hotter than the core. That physically doesn't make sense, but it's true. Let's just kind of jump over here and look at some of the numbers that we're going to be talking about. Number 4.6 billion years ago, the sun was formed from a spinning disk of gas and dust. The sun's mass is 330,000 times greater than that of the Earth's mass. Super, super large. And the sun is made up of 99.89 of all the mass in our solar system. So the sun makes up, once again, let's talk about that. The sun makes up 99.89% of the mass in our solar system. Super amount. And then this is an important amount too. We can see the exchange happening. The sun is made out of currently 73% hydrogen. Once again, it's fusing hydrogen and forming helium, so it's transferring over its mass. Law of conservation of energy. So it's transferring over, and at this rate right now, we have 25% helium in the core of the sun. Scroll down just a little bit. Whoops. Sunspots are caused by the sun's magnetic fields. So remember, they are brought up by the convection zone, and they create blemishes that then are magnetic. And so the sun can have lots of them depending on its cycle. Right now we're in solar minimum. About 11 years from now, we'll get into solar maximum, where it will rev up and there will be more. And then solar flares are sudden inbursts of energy that is released due to charged particles. And these solar flares can be really damaging to the Earth. We see them actually quite often. They're the ones that make the Earth's magnetic field vibrate so that we see the auroras. Most of the time, they just kind of graze right off our magnetic field, though. And then we have apparent magnitude and absolute magnitude. And apparent is just how bright stars appear to us versus the actual brightness of the stars. And we'll talk about this with the HR diagram when we move into a little bit of further pieces of information. So once again, I hope this information was helpful. Kind of a review of our layers. All stars have these layers. The sun's layers right here, just knowing what the fusion rate is. And then once again, going back through those stages of a star. Have a good day.